Guys, good morning. Here is a solution video for the Chapter 8 practice test. I'm going to complete the problems fully and then share this PDF with you so that you can use both the video and the PDF to make revisions to your work. So let's get started with the first problem. Factor the following expressions completely. Okay, factoring is going to require us to use a generic rectangle and a diamond problem for most of these. Okay, so draw your generic rectangle, diamond, x squared goes down here, 25 up here. 25 times x squared is 25x squared. Negative 10x is what goes down here. Two numbers that add to negative 10 and multiply to 25 are negative 5 and negative 5. Put that into your generic rectangle and find the length and the width. X minus 5, x minus 5. So then your answer will be x minus 5 times x minus 5, or x minus 5 squared. Okay, notice that this is a special type of quadratic. It's a perfect square case. How do I know that? Because you have the same length and the same width, so you get x minus 5 squared. That means it's a perfect square. We could have used a shortcut here. If you notice that negative 5 plus negative 5 is negative 10, and 5 times 5 is 25, you could have gotten this. But that's okay. It's always okay to just use the generic rectangle and the diamond. Let's do that for part B. But first, it says factor completely, and I'm noticing that we have a common factor of 2 here. So let's factor that out first. Okay, x squared, 8x, and 7. If I factor out a 2 from everything, that's what I get. Now I'm going to take this and factor it with a generic rectangle and a diamond. X squared, 7. 7 times x squared is 7x squared. 8x goes down here. What adds to 8 and multiplies to 7? That would be 1 and 7. If we put that back into the generic rectangle, we get our length and our width. So my final answer is 2 out front. That was the common factor. And then x plus 7 times x plus 1. Or you can put x plus 1 before x plus 7. That's okay. But that is our answer. Let's do part C. Right away, I'm noticing that 9 is a perfect square. Okay, it's 3 squared. I'm noticing that 49 is also a perfect square, 7 squared. And the fact that I have a minus here means that this is a difference of squares. Special case. I am going to use a pattern this time around because I can already see, visualize, where I'm going to put the 9x squared and the negative 49 in my generic rectangle. And when I multiply those, I'm going to get a really big number. So it's going to be a little bit hard to do the diamond factor. So let's just use the pattern here. Remember that for difference of squares, you have this number, so 3x plus, and then this number, 7, and then 3x minus 7. So the same factor, just plus and minus. So it kind of looks similar to your answer for the perfect square special case, but in difference of squares, you do have the plus minus. And if you want to double check that this works, please go ahead and do so. Let's see, part D. Let's use the generic rectangle and the diamond. 3x squared, negative 5. That would be negative 15x squared on the top when we multiply, and 2x on the bottom. What adds to 2 and multiplies to negative 15? That would be 5 and negative 3. When we put that into our rectangle, let's see, 3x times x gives us 3x squared. Where do I put 3x? Let's put it here because 3 goes into 3 and 3. Okay, x over here, x times 5 is 5x, 3x times -1 is -3x, and that works. Okay, x minus 1 times 3x plus 5. Okay, that is our answer for part D. So we're all done with the first problem. Okay. Number 2, graph the equation y equals x squared minus 6x plus 5. Label the y-intercept, x-intercepts, and the vertex. Hint, make a table of values to help you graph. Okay. Let's make a table. Sometimes it's good to get negative values of x in our table. So let's start with -2. Let's start with -1. And let's go out to like 3 and see where that gets us. Remember that to get the y values, you have to plug in x into the original expression. So I'm going to take y equals x squared minus 6x plus 5, and I'm going to plug in a -1 for x. So -1 squared minus 6 times -1 plus 5. That's going to give us, let's see, -1 squared is 1, minus 6 times -1 is a -6 plus 5. That turns into 1 plus 6 plus 5, which gives us 12. Okay, now let's plug in 0, and let's just go down the table. Okay, 0, 0, 0 squared, 0, 0, 5, 5. Okay, that was pretty quick. Let's do 1 now. 1 squared is 1, 6 times 1 is 6, 1 minus 6 is -5, plus 5 is 0. Okay, if you keep doing this, keep plugging in these values, when you plug in 2, you should get -3. When you plug in 3, you should get -4. But if you plot these points as they are, the -1, 12, the 0, 5, the 1, 0, the 2, -3, and then the 3, -4, you might not see a parabola yet. What that tells you is that you may need to extend your table or check your work. Our steps are good so far, so let's just extend the table. Let's add some more values over here so that we can see more points and see the shape of the parabola. Okay, again, keep plugging these numbers in. If you plug in 4 for x, you should get a -3. Let me double check the math in my head really quick. Okay, if you plug in 5, you should get 0. And if you plug in 6, you should get 5. So let's add those points. 4, -3, 5, 0, 6, 5. Okay, now we can see the shape. So let's connect these points. Draw arrows at the end of your parabola because it goes on forever. And let's label all the important points. Here is the y-intercept. I'm going to abbreviate intercept with int. And its coordinates are 0, 5. The x-intercepts are down here. Here's the first one, 1, 0. And the other one is at 5, 0. And last but not least, my vertex, the tip of the U shape, is at 3, -4. Okay, moving on. Number 3 says factor the following equation and then use the zero product property to solve for x. How are your solutions represented on the graph above? Okay, to use the zero product property, I'm going to have to factor first and then set each factor equal to 0. So let's factor x squared, 5 times x squared is 5x squared, -6x. What multiplies to 5 and adds to -6? You might be tempted to say 2 and 3. That doesn't work because these guys would need to be flip-flopped. What does work is -1 and -5. -1 times -5 is 5, and -1 plus -5 is -6. Okay. Find the length and the width. Okay, so now we can rewrite this as x minus 1 times x minus 5 equals 0. And what the zero product property tells us is anytime you multiply two factors and you get 0, one of those factors has to be 0. Okay? Anything times 0 is 0. So that has to be true here. So either x minus 1 has to be equal to 0, or x minus 5 has to be equal to 0. Okay, that's what the zero product property is, ZPP for short. And then you just solve for x, okay? I know I don't have to show you this step probably, but when we solve for x, we get x equals 1 or x equals 5. I say or because you can plug in 1 or 5 into the original expression and get 0. Okay. Part of this question was, how are your solutions represented on the graph above? I don't know. Where do I see 1 and 5 on the graph? I see it right here. They are my x-intercepts. My x-intercepts are at 1, 0 and 5, 0. It is no coincidence that those are my solutions for x. Okay. These are my x-intercepts on the graph. Okay, it was the same equation to begin with, x squared minus 6x plus 5, both in number 2 and number 3. So this is all to show you that ZPP, the zero product property, helps us find the x-intercepts of a graph, of a quadratic graph. Okay, pretty cool. Let's move on. Number 4, use the zero product property to solve the following equations. So following what we did up here, we need a factor first, and then we need to set each factor equal to 0 and solve for x. So let's do it. Generic rectangle, diamond, x squared, 16 x squared. -10x down here. What multiplies to 16 and adds to -10? That would be -2, -8. Okay, x times x is x squared, -2 here, -8 there. So you can rewrite x squared minus 10x plus 16 as x minus 8 times x minus 2, and then equal to 0. And just like we did up here, we need to set each factor equal to 0 and solve for x. So I need to set x minus 8 equal to 0. And I need to set x minus 2 equal to 0. If I solve, I get x equals, I don't have enough room down here. We'll make it fit. Okay, Okay, x equals 8 or x equals 2. And we are done with this problem. Okay, thankfully for us, part B is already factored, so all we have to do is set x plus 3 equal to 0 and x minus 5 equal to 0, and we get x equals negative 3 or x equals positive 5. Ignore the 2 here. When you're using the zero product property, you do not have to distribute it. You do not have to consider it in your work at all. Okay. All right, part C. You might be wondering, Ms. Ramirez, there is a 3 on the other side of the equation. It's not equal to 0. We can fix that by subtracting 3 from both sides. Okay, we get x squared plus 12x plus 27 equal to 0. Now we can factor. I'm going to do the rectangle and the diamond here on the side. I need to draw that bigger. Okay, x squared, 27. 27x squared, 12x. What multiplies to 27 and adds to 12? That would be 9x and 3x. Put that into your rectangle. X times x is x squared. 3 here, 9 there. So then this becomes x plus 3 times x plus 9 equals 0. Set x plus 3 equal to 0. Set x plus 9 equal to 0. And you get x equals negative 3 or x equals negative 9. All right, we've got one left for this problem. This is a perfect square special case. I already know because 9 is a perfect square, it's 3 squared, and 1 is a perfect square, it's 1 squared. And so when I factor this, I'm going to get 3x plus 1 squared equal to 0. Again, that's a perfect square case. You do not have to use the shortcut. If you want to use the generic rectangle and the diamond to factor this out, please do. You'll get the same answer that I did. And I don't want you to get hung up on the little details in the shortcut. I'm doing this to make the video a little bit shorter, even though it's like super long by now probably. But anyway, this is what I get when I factor. 3x plus 1 squared equals 0. Since we have something squared equal to 0, I don't have to set it equal to 0 twice. I only have to do it one time. So I'm using the wrong color. Not a big deal, but let's see. 3x plus 1 equals 0. So for x, subtract 1. 3x equals negative 1. X equals negative 1/3. Okay, really important tip here. For parts A, B, and C, notice that you have two solutions for x. How many x-intercepts will these graphs have? The answer is 2. Okay, for part A, your x-intercepts will be 8, 0 and 2, 0. For part B, your x-intercepts will be at negative 3, 0 and 5, 0. For part C, -3 and -9. For part D, we only have one value. What that means is that if you graph, I'm only going to have one x-intercept, and it will be at -1/3, 0. So what is that graph going to look like? Just like this. It's only going to cross the x-axis one time, and it's going to be at that one point. Okay? Just wanted to clear this up in case you see this in the future. Okay, number 5. Sketch a graph of the equation y equals x plus 4 times x minus 2. You can approximate the vertex. All right, when you use the zero product property to solve for x here, you set these equal to 0, and you get x equals -4 or x equals 2. These are your x-intercepts. Again, because when we use the zero product property, our solutions for x are those x-intercepts. Zero product property. Okay, so plot those points. -4, 0, and 2, 0. Really quickly, let's multiply x plus 4 and x minus 2 using a generic rectangle to get this into standard form. Let's see, let me add those terms all up, plus 2x minus 8. When I have an equation in standard form, which is this, blank x squared plus blank x plus or minus blank, this last term is my y-intercept. Okay, if you multiply an equation in factored form and you get an equation in standard form, that last term, the constant term, is your y-intercept. So I'm going to add that to my graph for accuracy. And it's okay if we don't know where the vertex is since it's just a sketch. So let's draw our parabola as best as we can. It's going to be pointing upward, I know that much, and coming back up like this. Okay, that's good. And let's move on. First of all, how did I even know it was pointing upward? Because, I mean, you can plug in points to check, but there's like an imaginary positive sign there. Okay, there's no negative, so I know it's going to be pointing upward. We're going to see something different for this last problem. Okay, number 6, last problem. Consider the graph at right. Is this graph opening upward or downward? This graph is opening downward. Okay, it looks like a frowny face. It's opening downward. What are the x-intercepts of this graph? That would be -2, 0 and 6, 0. So -2, 0 and 6, 0. Write an equation in factored form to represent this graph. Okay, guys, we're going to do the opposite of the zero product property. And we're going to go from the x-intercepts to the equation. So I'm going to have y equals x plus or minus a number, and then x plus or minus another number. What numbers are we going to use? We're going to use the -2 and the 6. Here's the thing though, I'm not going to write x minus 2 and x plus 6. I'm going to write the opposite sign. X plus 2 and x minus 6. Here's why. If I set x minus 2 equal to 0, I get x equals 2. Sorry, I wrote that wrong. If I set x plus 2 equal to 0 and I solve for x, I get x equals -2, which was one of my x-intercepts. If I set x minus 6 equal to 0 and I solve for x, I get x equals 6, which was the other x-intercept. So here you want to use the opposite sign. Here's one more thing, though, that we need for our equation. Okay. We need a negative sign. And here's why. Since this graph is pointing downward, okay, it's like sad face. Sad. When you're sad, you're feeling negative. And when you're feeling negative, when your graph is feeling negative, you need to put that out front, at least for factored form. Okay. So there we have it. Y equals negative parentheses x plus 2 times x minus 6. Okay, we were able to create an equation in factored form because it's kind of like the opposite of using the zero product property, and then we need that negative because the graph is pointing downward. All right, that is all. Pause, rewind, do whatever you need to do to look at these solutions, and let me know if you have any questions.